Okay, so I'm going to do a review of the alternative text, the Mitchell text, the ESRI Guide to GIS Analysis Volume 3. It has been assigned readings over the last several weeks. We haven't really lectured about it in class because the material is somewhat congruent to the topics that we've covered anyway. So in that sense, it's very much like a review, but we're going to go over it nonetheless. And over the next several slides, we'll cover a lot of material that will be on your final exam. Going to review quickly the modeling process. It's all about defining your goals. What are you going to do? Who's doing it where? What's the best? All these sort of questions, things that you're trying to figure out. That's how you decide or design some sort of analysis. Begins with defining a criteria that you're going to use to define what best is in terms of what you're looking for. So you establish criteria. You look at things like the consensus opinions of experts and pairwise comparisons. And ultimately, what you're going to do is take all these data layers that represent reality at some level. To them, you're going to assign weights. You might just need to go out and collect data because you don't have any. You'll run your model. And once you do, you can verify it, validate it, see what the result comes down, modify it, try again until you make a model that works. And this can involve something like sensitivity analysis, where we shift the weights in a complicated index model, or we change the way that we standardize variables, for example. Or maybe we change the way we combine individual data layers in a model. All of this is an interactive step, or interactive steps to the modeling process. So what are some of the keys to success? First thing you want to do is document what you're doing. You should sketch out some outline for how you plan to proceed with what you're trying to do. You want to display your results, see what it looks like, see if it's doing what you think it's doing, if it's giving you the information that you need, and then apply the model. And ultimately, like all good science, you need to engage and defend. In other words, once you're confident and comfortable with your model, you need to allow other people to have access to the model. And once they have access, you need to be able to defend the decisions you made and defend the model itself in terms of what you say it can do and what it actually does. Now, there's lots of problems with models. Some are too tall, some are too pretty, some make more money than you. Your friends are always hitting on them. That's not the kind of model problems we're talking about here. We're talking about a different set of model problems. We're talking about things like spatial bias and spatial autocorrelation and correlated layers and geographic extent and resolution and data quality. Specifically, we'll look at a few of these. Spatial bias, you need to be aware of it because it can cause problems. You must address it in the modeling process because it can interfere with your analysis. Spatial autocorrelation is something that occurs frequently, and oftentimes we're counting on it. But we have to understand the implications of what spatially dependent data is and what it means. Correlated layers, we have multiple data that may be unrelated to one another, but trend in the same direction. As one goes up, the other one goes up. And so you can have issues of multicollinearity, where things reinforce each other even though they may not be directly related. We also have to look at the extent and resolution. Sometimes analysis tells us where and what we have to do. And where we're doing it might tell us a great deal about these other things, and these can all impact the decisions we make, the outcomes we get, and ultimately our models. And lastly, of course, data quality. You need to be ready to defend decisions about what you say is acceptable or non-acceptable data. Simply, it was the first data I found is not good enough. Professional setting, if someone asks you why you didn't use better data or different data, you need to be able to answer those questions. So here are some examples we're going to look at of some data, different ways you can look at these different clusters and groups, and different ways of showing things. Different colors could mean different things to different people, and by using the these point distributions, it makes some areas look more important and some areas look less important. But you have to be aware of the impacts of these things on what you do. When we talk about things that are correlated versus causal, this is a really good map I like to quote from time to time, where we look at the approximate number of pirates in the world versus the average global temperature. And you can see that there is a strong linear correlation between the number of pirates and global warming. And so the clear understanding for some people is pirates cause global warming. That is not the case. What this illustrates is that just because two things track with one another does not mean one causes the other. Now, if this relationship is constant and steady and we know it and we're reasonably confident that it's going to continue, maybe we can use the number of pirates to predict future temperatures. But there's no guarantee that this trend will continue because there is no scientific or physical logical rationale for why one is related to the other. And in fact, it's probably just a spurious correlation. There's some more data we can look at. This looked at how the number of financial disagreements related to husband and wives and how it related to the increase in the number of divorces. What does something like this tell you? It doesn't tell me a lot. When they're modeling things like this, you have to figure out how to present your data so that it makes sense. The crux of most modeling really falls back to the concept of a basic suitability model and how we can apply that to other things. When we talk about basic suitability models, we're talking about things like finding locations for a specific use. In other words, you're going to define a problem or a criteria, choose tools, and you're going to use logic, and you're going to collect data and make selections and evaluate results and display and apply and do all these things until you basically identify a location that meets some criteria. The specifics of what you're doing, the order should not necessarily matter. You want to do things to make your model efficient. Things like if you have layers that will eliminate vast amounts of data, you want to do those things early in the modeling process so that you're not chugging through and processing large amounts of data that ultimately you will not need in your model. You want to do things like sensitivity analysis, or at least a rudimentary version of it, where you change variables, you change weights associated with various things to see how changes in variables affect how it affects your modeling output. Ultimately, you can use these sort of things to evaluate your output terms, weights, and other variables to determine if you have the correct specifics in your model. And lastly, there's the techniques. Are you going to be creating derived layers? You're going to use overlay functions, map algebra, raster calculations, reclassifications. What tools and or techniques will you employ in your model to ultimately get to that question of, does this location meet my criteria? How do we rate suitable locations? It's not always just yes and no Boolean sort of scenario. A lot of times we're not looking for whether something meets a minimum threshold. We want to be able to rank things so that we can identify the best option. So if we're going to do this, we have to decide what's important. We have to classify our data, standardize it so that variables are on similar scales. We have to rank them in terms of what matters and what doesn't. And then we have to apply, what we need to do to get the results we're looking for. And we can do this using weighted averages or weighted models or weighted parameters. We can use fuzzy overlays where we have complicated mathematic functions relative to data, because maybe we're looking for a south-facing slope, but south itself isn't so much important as it needs to be south-ish. And so maybe it's not just an aspect of 180, maybe it's an aspect between 150 and 210. And so you have to decide that. And in that same scenario, 210 and 150 are neither one of those are as good as what 180 is. So you come up with a sliding scale where you can generate outputs that allow you to have some degree of selection or success. And lastly, you don't have to pick just one technique. You can combine techniques, but you have to do so with great caution. And it's not just in red letters and bold print because I like red letters and bold print. It's because I'm serious. You can mix and match these things quite a lot, but there's certain things you can't really do, like change the different standardization techniques between your variables. Because if you don't use the same technique, for example, then you're really not standardizing them. So that's just something to be aware of. So how do we create these suitability layers? Well, the first thing you got to do is standardize your data. Or not, depending on what you're trying to do. You can rank your data, but if you rank it, you're really standardizing it. You can also weigh variables, but if you do that, it's sort of another way of standardizing it. But ultimately, you need to have your variables in the same format. If you use multiple standardizations, you're somewhat weighing in model terms, but it's not really the way you want to do it. So you want to select a single standardization and then stick to it. If you're going to use a single scale, that works great. Commonly when we use scales, we use things with 3 to 9 categories. Exclusion is your best friend. Don't be afraid to use Boolean layers as an exclusionary layer to eliminate some locations. Run virtual what-if scenarios. Create alternative scenarios. Evaluate your model, your weights, and everything to generate other models to figure out which model is the best. It's not quite the same thing as sensitivity analysis, but it's similar. It's really about conducting and constructing your models in different ways to make sure that your model more perfectly does what you want. You can assign weights and you can combine layers. And there are numerous options to how to do this. It'll be talked about later. But they're all very important components in creating suitability layers for a suitability model. I'll talk a little bit more about the fuzzy logic side of things. We covered this back at the beginning of the semester. We did some examples in the whiteboards. I'm just going to vaguely and quickly cover over it here. Fuzzy overlays rate locations continuously based on many layers or inputs, all of which need not be fuzzy. It's based on this concept of logic of theory sets and sometimes called fuzzy logic. And so the easiest way to kind of understand it is to think of a scale from 1 to 10. And 1 is misting rain, and 10 is like a 500-year flood level monsoon downpour rainstorm. Fuzzy logic is just a mathematical way of numerically defining how rainy it is. And you use these fuzzy membership functions as opposed to asking a 1 or 0 yes or no Boolean question of is it raining or is it not raining. We want to know how much it's raining, and so we can use a scale like this to do that. Observed values, if you set to 1 and 0, most likely everything is 1 or 0. But in general, observed values are not 1s and 0s. For the most and least likely to occur, everything else is usually somewhere in between. It's generally some degree of whatever the thing is that you're observing. In categorical data, if you have 25 categories, rank them from best to worst and assign values of 1 and 0 to either ends of the scale. What if it's somewhere in the middle? Well, you can rank those evenly between those two values, and maybe you want to put an exponential scale on that. You could do that in how you rank the data. Sometimes categories are similar and the differences should be minimized. So maybe you've got 10 categories and 6 of them have the same weight, but the others do not. So you have to think about these things. They're not trivial decisions. Continuous data is better to define a mathematical function to calculate values than what other stuff is, because it does the smoothing and and continuous nature of continuous data allows for greater differentiation when we're selecting better and best as opposed to selecting meets a minimum requirement. I'm going to talk a little bit about the networky stuff, and then, yeah, I know it's not a word, but network analysis is already a drab enough topic. We need to try to inject some humor into this work when we can. So we'll talk a little bit about network paths. This is things that you use for infrastructure, transportation, and flow, understanding of time, and the connectivity between locations. So how does the process work? Similar to a lot of other GIS stuff. Excuse me. Let the record show that I am putting this video together at 6:08 a.m. in the morning, primarily due to insomnia. But just as good a time as any to get the work done. So here we go. First thing you're going to do is define your problem. Some problems are very general in nature and some are very specific. Either one could be things that you need to understand as far as the process that you're going through. You just set the parameters and select your data. Common parameters when we look at networks are things like cost. What is the cost of traveling on this network? Direction. What direction can I travel? Are there barriers, things that prohibit certain movements? Some of these things are found, and some of these things you're going to have to make. Next, we're going to talk about creating a network layer. Network layers are basically a collection of edges and junctions representing physical infrastructure. And so it tends to be the locations where you can go and where you can't go, and the things that stop you. And then there's simple cost layers like elevation that you can use. You can also put costs and restrictions. And so, for example, you could place a restriction on roads indicating minimum and maximum speeds based on the slope of the road. If it's too steep going up, you can't maintain higher speeds, and if it's too steep going down, you have to go slower or else your speed will become unmanageable. The number of lanes in a highway can restrict the flow, speed limits. You can also have things like soil type that could restrict movement because maybe it's not a stable soil. It's something that with heavy truck traffic would quickly lead to being stuck. Maybe vegetation is a restriction. Certain vegetation you can walk through easily, other you cannot. It's a lot easier to march across a mature forest than it is across a wetland. So these are the kind of things that you can assign restrictions and costs traversing the area, so that when you do analysis on a network, you can then more accurately estimate the cost or the time that it's going to take to go from point A to point B relative to the changes in the surfaces that are between the two locations. Ultimately, it's all about solving the problem of how do I get from here to there, given all these other things that I'm worried about and concerned about. Talk a little bit about some of the stuff maybe you didn't know. Overland travel, you can calculate distance over terrain, not just as the crow flies, because it's not always the exact same thing. You can change cost to reflect the weight of your pack. So you can make your load heavier to show that it's a harder hike. You can map the fastest, and the fastest when you're loaded is not necessarily the same as the fastest when you're unloaded. You can also do things like map the shortest. So there's a lot of creativity that can come into play using network analysis that will allow you to identify really unique and useful information. Cost surfaces are just that. They're typically a raster surface that assigns some cost to individual cells. In other words, to go across this cell, there is a cost. Is that a cost in time? Is it a cost in effort? It doesn't matter. It's a cost. Typically, the ratio, they're measured meaningful, and they have to have a meaningful 0 point. Overall cost surface layers are things like combined costs for multiple factors. It could be described as a model in and of itself, but that's an entirely another argument. If you want some specific examples on these sorts of things, review back to the chapters you read in the ESRI Guide to GIS Analysis Volume 3, particularly focusing on pages 1 through 268 for many in-depth and quality examples. I'm We're going to talk a little bit now about chapters 5 and 6. We're going to kind of have a 70-30 breakdown on flow and on interaction. We're going to cover the basics. And if you have specific interest on these things, I strongly encourage you to go back and read these chapters again in the ESRI Guide to GIS Analysis Volume 3. We talk about modeling flow. There's really sort of three things that go into it. You have to design a flow model, which means you have to know what the problem is, and you have to understand what influences flow, and you have to figure out or understand over what sort of time we're talking about. Once you do this, you can begin to model accumulation, and you do this by obtaining elevations, figuring out flow directions, and other required outputs that you're going to get from that, and ultimately evaluating how flow accumulates across your surface. You can use this for a lot of things, like tracing flow over a network. You can specify the geometric network for what this happens. You can set flow directions. You can trace things and evaluate and display stuff, and you can learn a lot about how flow occurs through this modeling process. So we'll talk a little bit first about designing a flow model. The problem is the first step. Why are we doing it? Why is it important? What are we trying to actually understand? What influences it? So what sort of things do we need to look out for? And then what kind of time frame are we looking at? Most models address where the flow goes, what it travels over, or what areas is affected, or how far it travels, or how long it takes to get there. Physical factors that we worry about related to the phenomenon are external factors. They're not necessarily related to the physical process. They're just the landscape. Everything occurs over time, so you need to set, identify, and consider time in models as to whether it's an important component or not. I want to talk a little bit more about flow accumulation. This is mostly used in hydrology. This is how we identify where water flows and accumulates on a terrain surface. There are lots of methods, and each method impacts the output. In general, it's a four-step process. You find an elevation surface that you're going to work with. You create flow direction by identifying areas that are up and down slope of a given location. And then you're going to create specific required outputs based on those to calculate the hydrology that you're interested in, and then ultimately evaluate the results. It all starts with a digital elevation model, or a DEM. Sometimes we toss these words around interchangeably: DEM, DTM, DSM, etc. So we want to look at this in a little more detail to make sure we always understand what we're talking about when we talk about these specific elevation models. Think of a DEM as a grid in which every cell is the elevation of the terrain at the center of that cell. So we have a nice illustration in the top right hand corner of the screen indicating the difference between a digital terrain model and a digital surface model. Now, a digital surface model is literally the surface of all the features there. Houses, it's the top of the building. If it was a tree, it would be the top of the tree. In other instances, it's the surface of the ground. Now, a digital terrain model is different in that the terrain model excludes things like houses and man-made structures, and it looks at the digital face of the earth, if you will. And there's a nice picture of what a digital elevation model or a digital terrain model would look like in the bottom right-hand corner. Flow direction is based on a specific flow routing algorithm. It determines the direction of flow from each cell. And the first step is you have to have a sink that is, or a DEM that has no sinks. And the reason is flow accumulation, flow direction, flow calculations, and most of the hydrology that we do is contingent upon the basic construct that all water must exit the watershed. And it's all about the direction of overland flow, and instances that relate to immediate movement of water down through the soil profile as opposed to across it don't work for us. So we can't do all this fancy hydrology stuff if we've got a lot of sinkholes, or just perhaps it's not even sinkholes, perhaps it's just errors in the DEM. So we have to fill these points, because the fundamental premise of flow accumulation and flow direction is that every cell in the digital elevation model drains to somewhere. And so that's what we do. A sink is a depression in elevation with no outlet, and so we have to fill the sinks and basically raise them up till they reach an elevation to where they are no longer lower than all their surrounding cells. And then we can proceed with hydrology analysis. So here's sort of how this works. You have an elevation surface. From that, you calculate a flow direction. And the flow direction uses a different coding system, and here in the bottom you sort of get an idea. If things are moving down to the right, it's a 2. If they're moving to the right, it's a 1. If it's moving straight down, it's a 4, etc. And so then you code that into another raster layer, where instead of having an elevation in each cell, it has a directional indicator in each cell. And that is essentially what flow direction looks like. Now, how do we actually calculate that? Oh my goodness, there's a bunch of ways we can do that. Read all this stuff, commit it to memory. No, I'm just kidding. Read through some of these things. There's lots of different ways to do it. I'm not going to go through a whole lot, but in general, I'm going to look at a couple examples. The first one here is a single flow direction, or a deterministic 8 method. And in something like this, every cell has to flow to another cell, and then the content of that cell goes entirely into the one cell that it goes into. And so everything goes to its lowest or its steepest downslope neighbor. Once that neighbor is identified, its entire contents and volume is then allocated to that cell. And you get things like the one at the top. Now, the bottom right, there's something called a multiple flow direction. Multiple flow direction does not assign flow strictly based on what is my steepest downslope neighbor. It divides flow amongst all of the downslope neighbors. It does it somewhat proportionally, so it doesn't necessarily just throw it all in one. And there's different ways of calculating it, but you can see how on the top you only have one direction, and in the bottom illustration things go in multiple directions. Ultimately, they all end up down there in the bottom right corner at a value of 35, but how it gets there is very different. And the net impact of that, if you look at the two images at the far right, is you get a much more blurred, a much more smooth hydrological output. So we'll talk a little bit about this again, make sure everyone understands what we're doing. This is a two-dimensional illustration of a digital elevation model, and we have a specific flow routing algorithm, regardless of what it is going to then determine where that water would flow if it was poured on that top cell, represented in this case by a column. It would go to the one below it, and then the one below it, and the one below it, and the next one. The problem is that one wouldn't go anywhere because it is a sink. And so before we could do any real hydrology, we have to make sure that this DEM is free of sinks. And so we would do that. Now the problem is there are actual sinks, things like lakes and ponds and oceans. There's also areas that are just relatively flat, and that can create problems as well. So how do we do this? Well, the first thing you do is acquire a DEM, and then you fill the sinks. And there's lots of different algorithms for doing this, but you need to understand the implications of what you choose when you do these calculations. In other words, fully explore the help section and even check out sources like Wikipedia and other websites to determine what you don't know about a data set, and then select the data set that most closely meets your needs. In other words, maybe select the data set is really not the right way of phrasing it. You're going to create a data set. You need to select the algorithm to do that that gives you an output that you're most comfortable with, you understand, and is most useful for what you're trying to do. Ultimately, you're going to use a lot of these data layers that you create, not for what they are, but for how they are folded into, are built upon, are required for the creation of other layers and the development of other more complex levels of knowledge. So here we got an example. This is a D8 model, and it gives you very much a linear sort of feel to the hydrology. When we go to a multiple flow direction, we get a much smoother version. Ultimately, there's something in between called deterministic infinity, where we don't force our flow to divide amongst all of our lower sloped neighbors, but it does proportionally assign it to one or two. And if it's a steep enough difference, it all goes to 1. And so you get something that is not as irregular and granular and unnatural looking as the D8, but it's also not as smooth and vague as the multiple flow direction one. That was the second image we looked at. How do we determine where channels is at? Flow direction facilitates flow accumulation. Once you know the direction, it's simply adding up how many cells are upstream in my network. Delineating drainage channels is based on the number of cells that have to accumulate before you consider something a stream. In other words, you identify a value threshold of accumulation that then indicates a stream channel. Um, so this helps you figure out when something actually becomes a stream. A channel in general is only one cell wide and is difficult to see, and it is very raster-like. And so oftentimes once you identify these things, it's best to convert them into vector, into a linear feature, not a grid-based feature, because it will be much better for the other analysis that you do later on. Drainage areas. Now that you have a stream, you want watersheds. Pour points. Can be for points or segments of a stream. They work pretty good, but it can be kind of sketchy because it's really hard to hit the point where you want. Segments are easier to work with. You can snap pour points to flow accumulation layers, but you have to set the search radius, so you need to play around with it. It's easier if you're in ArcGIS to calculate basins than it is to identify watersheds by pour points. So why do we do a lot of this stuff in raster? Remember, raster is faster, but vector is correcter. So why do we do it? Well, if you have a watershed in raster format, it's easy to calculate areas, and it's easy to do a lot of things. Once you know the number of cells, you can just multiply it by the cell size squared. Throw in some unit conversions, and voila! You know exactly how much area you had. Zonal geometry is another tool we use a lot. This allows you to calculate areas for each drainage or for other stats, and so basically you have one data set that has information you're interested in and another data set that defines the zones, and then you calculate or summarize or statistically analyze data in the first data set relative to the delineating factors in the second. So how much flow? How do you calculate flow volume? You need a weights layer. Weights can be simple as multiplied by expected rainfall over an amount of time. You can summarize it. There's lots of different ways. In general, more advanced hydrological models would consider things like vegetation and soil and slope, because that is directly related to how quickly rainfall becomes runoff. That relates to how much rainfall infiltrates the soil and how much is overland flow. All these complicate how water will accumulate. Ultimately, most of the hydrology stuff we do in ArcGIS really is about telling us how it will accumulate, not so much as defining how it accumulates, because to do that you literally have to have enough of whatever your thing is you're measuring, in theory, to run through, fill up your model, and come out the other side. And so if we're thinking about things like rainfall, it's really hard to judge how rainfall relates to discharge or flow until you have enough to actually overwhelm your surface and generate that. So it's difficult. Why do we do it? Well, it's important. It allows us to estimate runoff. We can predict sediment and nutrient loads in surface water by determining how much water from a given rainfall event will go across the land and how much will go down through it. And that helps us understand how nutrients that are surface applied, for example, will move around. When we also have land that has been tilled in farms that are that don't participate in no-till practices, we can get some better idea of the soil material that can be more easily discharged from the location with heavy rainfall, because we've plowed it all up. We can also model travel time, which can be very important when we look at things like contamination events, that sort of stuff, to figure out how long it takes to get there. We can also use all these things to predict peak flood stages, and so it'll help us understand not just how high the water's going to get here, but when, where is it coming from, because that can help us identify other streams that might be flooding as well. Talk a little more about networks and tracing flow in a network. It basically requires a geometric network, which means you have to have built-in considerations, specialized weights, and then rules that define how these things occur. The two common ways to set flow direction in a network is to digitize the direction of the edge networks. ESRI has a tool for displaying the edges and flipping them when you want flow to go in a different direction. You can include sinks and sources in the design. A sink is where networks converge. A source is where something that pushes flow outward. You can trace these things to model your networks. You can use barriers to confine to trace, and you can multiple origins when you're doing this if you want. We'll talk a little bit now about interactions. When you think about interactions as a spatial aspect of why people and things behave the way they do, things do not occur generally in isolation. If you're familiar with the Douglas Adams character of Dirk Gently, the holistic detective, and the idea is that everything in the universe is interconnected and related, and that things don't happen in and of themselves, and there's this complex interaction between things that make the oddest things become related. Now, I'm not saying that that's right, or that's even a philosophy for life. What I'm saying is, when we deal with models, spatial models, GIS models, we're often dealing with this multiple layers of data, and there is interactions. So when you're thinking about it, there's a basic idea to think of two types of models. One is to model what you have, and one is to model what you want or what you need. And the interaction is the stuff that controls the movement or selection between these two models. Another way to think of interaction is a spatial choice model. You identify locations of fixed things, and you model the choices people make to select from the fixed things, like which way to go. And for example, that's a spatial choice model. So what's this process of modeling interactions look like? You define the problem. What types of model do you need to answer your question? You have to understand your problems at a very high level. You have to have a deep and thought out understanding of what it is you're trying to answer in order to construct a model that's going to work. You need to ID things like the facilities and demand points in a network like this. Facilities are locations that produce or provide. Demand points are places that consume or utilize things. So imagine we're talking about a traffic network. Locations that produce or provide would be places where traffic egresses onto the network. Demand points are places that consume or utilize something. In terms of travel time, this could be places like stoplights and such. You have to determine the influences on the interaction. How do these things impact the cost of travel? How distances should be calculated? Because if we're talking about linear distances, then a lot of these things don't make a big difference. If we're talking about a cost in terms of time, then they make a pretty big difference. Ultimately, you need to define your solution. Your model should be designed to give you the answers that you can use and the ones that you need. You have to understand your existing conditions. Are you looking for one solution, multiple solutions, a scored solution surface? These are all the things you have to think about. What are the constraints and limitations on what you're trying to do? Are we worried about distance? Are we worried about time? Are we worrying about the expense? You need to think about these things. Ultimately, as you understand these better, it will help you set up a network topology. You think about the topology, the connectivity, the direction, the impedance, the cost, surfaces, the weights. All these things need to not just be set arbitrarily, they need to be set to reflect the physical reality of the environment you're trying to model. Specify facilities and demand points. We talked a little bit about that. Running your model, basically, it's the shampoo method. That's what I call it. So rinse, wash, repeat. Rinse, wash, repeat. Rinse, wash, repeat till your hair is clean. That's sort of the way it is with this modeling. You're going to create a model, and then you're going to run it. You're going to give it a try. You're going to tweak it. You're going to tune it. You're going to make it better. You're going to make it special. You're going to make it dance. You're going to run it again. You're going to play around with variables and thresholds and weights. Tune it up. Run it again. You're going to see whether certain things changed in combination, create outputs you're not happy with. You'll run it again. And at some point in time, you'll reach an understanding with your model where it does what you want it to do. Of course, all the while, we expect you to follow good GIS methodology, not just be punching things in for the hell of it, but to try to make the right choices. So there's specific types of these models. There's lots of them. If you go to page 365 in the text, there's more information on this than you can check a stick at. So you can go in there and look at these things in some detail if you're interested.